exam. Okay. It is set B question paper, Aero and Flight Mechanics. In that first question, question number 12. What is the differential pressure of an airliner cruising at 35,000 feet, cruising at 35,000 feet with a cabin altitude of 8,000 feet, with a cabin altitude of 8,000 feet. Okay, with a cabin altitude of 8,000 feet. First, we have to convert feet into meter. So, what is that? 35,000 feet they have mentioned. We know that 1 feet is nothing but 3048 meter, 0.3048 meter. Sorry, 1 feet is equal to 0.3048 meter. So, it is, if you have to convert it to meter, it is 0.3048 multiplied with 0.3048. So, 35,000 into 0.3048 will get it as 1668 meter. Then cabin pressure it feels is 8,000 feet. So if I convert this into meter, 8,000 into 0.3048. So it is 2438.4 meter. 2438.4 meter. So let me consider this 8,000 feet as T1, like altitude H1, and this is H2. 35,000 is H2. Okay. Now, corresponding to the altitude, we have to find out what is the temperature. What is the temperature at T1? T1 is T0 minus lambda H1. 8,000 feet. It lies in the uh, both this altitude from 0 to 11,000 meter altitude, 11 kilometer altitude. It lies in the troposphere. So both the layers are in troposphere. So we can use troposphere relationships for both the things. Because 0 to 11 kilometer altitude, it's a troposphere. Okay. So T naught is sea level temperature, which is 288.16 Kelvin. Lapse rate is 0.0065. H1 is 2438.4 meter. Substituting that, I get temperature as 272.3104 Kelvin. So T1 is 272.3104 Kelvin. Now we have to find out what is the temperature at T2 altitude also. What is the temperature at T2 altitude? It is T0 minus lambda H2. So 288.16 minus 0.0065 into 10,668 meter. So we get the value as 218.818 Kelvin. So this is T2. Now we have to find the pressure at these two altitudes. So We use the other relation, troposphere relation, that is P1 by P naught is equal to T1 by T naught power G by lambda R. P1 we doesn't know, we have to find out. P naught we know, it is 101.325 kilopascal. It is in kilopascal, sea level pressure. T1 we just found out, which is 272.3104, 272.3104 divided by 288.16 Kelvin. Acceleration due to gravity at sea level is 9.80665 meter per second square. Lapse rate is 0.0065 and gas constant is for air is 287.026 joule per kilogram Kelvin. Substituting that, we get the answer as so P1 we get it as 75.26 kilopascal. 75.261 kilopascal. Now we have to find out what is the P2. P2 by P naught is nothing but T2 by T naught power G by lambda R. P2 we doesn't know, but P1 we know. P naught we know that it is 3001. Sorry, 101.325 kilopascal. That is equal to T2. We know that we have just found out 218.818 Kelvin. 218.818 Kelvin. T naught is 288.16 Kelvin. So G value and lambda value all are remaining same. Okay. So we get P2 as 23.840 kilopascal. 23.840 kilopascal. So the differential pressure felt on the wall is 75.261 minus 23.840. So it is 51.421 kilopascal. So the nearest answer, which is as per the given data, is option B is the correct answer. Option B is the correct answer. So, what is the differential pressure felt by the cruising airliner at 35,000 feet with a cabin altitude pressure of 8,000 feet? This is the differential pressure we needed, 50 kilopascal. So, we'll move on to next question. Question number 16. Which one of the following requires aerodynamic heating? So for aerodynamic heating to occur, it requires supersonic or hypersonic flow. Supersonic or hypersonic flow, because both supersonic and hypersonic flow only can generate shock waves. So through shock waves, across the shock waves, the temperature increases, pressure and temperature increases across shock wave. Pressure and temperature increases. SW is nothing but shock wave across shock wave, because supersonic and hypersonic flow only can create shock waves. Across shock wave, pressure and temperature increases, which causes aerodynamic heating. So, for aerodynamic heating to occur, you require a supersonic flow. Okay? So, option B is the correct answer. Question number 40. Which one of the following is the maximum distance between mean camber line and the chord line measured in perpendicular direction to the chord line? So, if you take an aerofoil, consider this is an aerofoil, cambered aerofoil. The line joining leading edge and trailing edge is called as, this is the leading edge of the aerofoil, this is the trailing edge of the aerofoil. The line joining leading edge and trailing edge is called as chord line. This is the chord line, and this distance is called as chord. The midpoint between upper surface and lower surface, the midpoint between upper surface and lower surface of the aerofoil. If I draw a midpoint between upper surface and lower surface of the aerofoil, this line is called as camber line. The maximum distance measured perpendicular to the chord line between mean camber line and chord line is called as camber. So, option A is the correct answer. Option A is the correct answer. Okay. Question number 41. Consider the following statements regarding aerodynamic efficiency. Okay. The maximum lift to drag ratio is an important parameter in aerofoil performance. It's a direct measure of aerodynamic efficiency. The next statement given is, higher the value of L by D max, more efficient is the aerofoil. The value of L by D for aerofoils are quite large numbers in comparison to that of complete aeroplane. So, if we take the first one, yes, it is also one of the important parameters in calculate. It is also one of the important parameter in aerofoil performance, because for an aircraft to be having better range or endurance, so the aircraft to have better range in different class of aircraft or endurance, we require CL by CD max condition. For propeller engine aircraft, CL by CD max condition leads to maximum range. That is L by D max condition. L by D max is non-dimensionalized form. It is CL by CD max. For a propeller engine aircraft, it is giving maximum range. CL power 3 by 2 by CD max condition gives maximum endurance of propeller engine aircraft. Same thing for jet engine aircraft. For jet engine aircraft, CL by CD max condition leads to maximum endurance. CL power 1 by 2 by CD max results in maximum range. So your minimum drag condition, L by D max is nothing but minimum drag condition. So minimum drag in an aircraft is a more essential parameter. L by D max is one of the aerodynamic efficiency. Okay. So while selection of aerofoil, they give various criteria for selection of aerofoil. What are the criteria? Is like CL max, alpha stall, CL by CD max, CL power 1 by 2 by CD max, CL power 3 by 2 by CD max, moment coefficient. So all these performance parameters, we give weightage factors to select what is the aerofoil required for our requirement. So if it is maximum range of propeller engine aircraft, then you have to select CL by CD max condition to give more weightage for this. Then based on the weightage factor given to all these factors, based on that we'll select an aerofoil. So in order to select an aerofoil, this is one of the important parameter, and it is also direct measure of aerodynamic efficiency, because aerodynamic efficiency is nothing but CL by CD, CL power 3 by 2 by CD, and CL power 1 by 2 by CD. All these are aerodynamic efficiencies. Okay. So selecting one is more important. And most test books, only L by D they selected this as aerodynamic efficiency. But all these parameters are, few test books select CL by CD only as an aerodynamic efficiency. But most time, all these three parameters are aerodynamic efficiency. If L by D is max, the more efficient is the airfoil. Yes, L by D is max means you have drag minimum. That means you have more performance, better performance. So then this is also correct. What happens if you see the value of L by D of aerofoils are quite large in comparison to that of the complete airplane. If you see only aerofoil, if you see only aerofoil, the flow was only occurring in the chordwise direction. Flow is only occurring in the chordwise direction. So there is no induced drag. No induced drag. So since there is no induced drag, only profile or parasite drag is there, which implies no induced drag means no profile or parasite drag. No profile or only profile and parasite drag is present. That is only parasite drag is present, which implies only parasite drag is present. That means this will have least drag. The airfoil alone configuration will have least drag, which means L by D will be very larger, far larger value. Okay, L by D will be far larger value. Okay. But if you take a 3D wing, what happens? When you take a 3D wing, there is not only chordwise flow is occurring, there is a spanwise flow is also occurring, which causing wingtip vortices. Which causing wingtip vortices. This results in wingtip vortices results in downwash. This further results in induced drag. Okay. So there is an additional drag component. Apart from that, your profile, your parasite drag also increases because surface area increases. Parasite drag also increases because surface area increases. And apart from that, there is also a factor called as induced drag. Combinedly, drag is drag of an aerofoil, if you see, drag of an wing, if you see, drag of a wing is far greater than drag of an aerofoil, which means L by D for the wing will be far lesser than the L by D of a aerofoil. So L by D of an aerofoil will be a larger value. L by D of the wing will be a smaller value. L by D of an aerofoil can go more than 100. It will be 150, 160, or 200. It can go more than 100. So it can be more than 100. But L by D of the wing, it will be around max to max, it will be around 15 to 20 or 25. So L by D of an aerofoil is a larger value compared to that of the complete airplane. I have taken only wing alone there. If you take entire airplane, there will be interference drag also. So, which causes more drag. Okay. So this is for wing alone. The L by D is 15 to 25. For the aircraft, it will be further less than value, which is around 5, like 10 to 15. It will be around 15 to like more than 20 to 25. Here it will be 10 to 15. So further aircraft's value is further decreased. Further the aircraft value is further decreased, which means that L by D for the aerofoil is far larger value. So that statement is also correct. So which of the above statements are correct? 1, 2, and 3. All the three statements are correct according to the given question. Okay. Next. Question number 42. The flow field is defined as supersonic if the Mach number is 0.5, the Mach is 0, the Mach number is less than 1 at every point, Mach number is greater than 1 at every point. If Mach number is 0, then the flow field will have 0 velocity. Flow field will have 0 velocity. 0 velocity. Which implies Mach number is also 0. Because Mach number is nothing but velocity by speed of sound. Velocity of aircraft by speed of sound. A is nothing but speed of sound. Okay. So Mach equal to 0 implies velocity is 0. So the flow field is having standstill. There is no flow field at all. Flow field is standstill. There is 0 velocity, 0 Mach number. So this cannot be the case. Mach number is 0.5 means it's subsonic. In a subsonic condition, the flow field cannot also be supersonic. The flow field cannot be supersonic. It can also be subsonic only. So this is also wrong. The Mach number is less than 1 at every point. The Mach number is less than 1 at every point means it is also subsonic. Only at only when the critical Mach number is reached, the flow field can be supersonic. That also complete flow field cannot be supersonic. Only at the range where curvature is present. Only in the curvature area, the flow will be supersonic at that region at critical Mach number, except that remaining all the places it will be subsonic flow field only. So this cannot be also correct. Below critical Mach number, all the flow and flow field is only subsonic. Only at critical Mach number or above critical Mach number, there is a supersonic condition is reached. Only at that point, only at the point where the highest curvature is there, flow acceleration is happening. Only certain region of the flow field will be uh, supersonic, but complete flow field will also not be supersonic. If Mach number is greater than 1, Mach number is greater than 1, that means if you take any point in a flow field, this I have talked in reference to aerofoil alone, but if you talk in a flow field, at any point if you take A or B or C, any point if you take, all the point will have Mach greater than 1 only, which implies it's a supersonic flow field. So the flow field is defined as supersonic only if the Mach number is greater than 1 at every point. So option D is the correct answer. Okay. Question number 43. If m is the local Mach number at an arbitrary point in a flow field, then by the definition, the flow is locally supersonic if then by definition the flow is locally supersonic. Okay. They have not mentioned here an aerofoil. If there is an aerofoil, of course, it can be less than 1 also, because now only I explained at critical Mach number, the flow field locally can become supersonic. Mach less than 1, which is around approximately zero point 0.6 to zero point 0.8, somewhere on the top surface of the aerofoil reaches Mach equal to 1. So at this Mach number, the so example, if you take 0.65, around 0.65, on this aerofoil it reached Mach equal to 1. That is called as critical Mach number, which occurred at Mach less than 1 only, critical Mach number. But they have mentioned an arbitrary point in a flow field. They have not mentioned uh, like they have not mentioned anything regarding aerofoil or something like that. If m is the Mach number at an arbitrary point in a flow field, then by definition flow is locally supersonic if Mach is equal to 1. If Mach is equal to 1, there is a flow field. They have not represented whether there is a body or not. So if we take any point, any arbitrary point, there also flow field will be sonic. Mach equal to 1 is called as sonic. So option A is the correct answer. Okay. Question number 59. Consider the following statements regarding aerospace vehicles. Aerodynes produce lift by moving the air through moving a wing through an air. What is called as aerodyne? It is heavier than air aircraft. Heavier than air objects are called as aerodynes. Heavier than air objects are called as aerodynes, which including flying vehicles. I'm talking heavier than air flying vehicles are called as aerodynes, including airplane, your rotorcraft, that is helicopter, or glider. Okay. So these objects are called as aerodynes. Aerodynes, how they produce lift? By moving through the air. By moving through the air only they produce lift. So this is a correct statement. Aerodynes includes fixed wing aircraft, rotor aircraft, and are heavier than air aircraft. Yes, aerodyne by definition itself, they are heavier than air aircraft. So option 2 is also this statement is also correct. Aerostat is a craft which is lighter than air aircraft. It is lighter than air crafts or lighter than air vehicles are called as aerostat. Example, your air balloons. Example, air balloons. So is a craft that aloft. Aloft means it stays in air primarily through use of lighter than air gases, which produces lift to the vehicle with nearly the same overall density as air. Okay. So whatever the difference in density that produces you as lift, that is called as aerostat. Okay. So third statement is also correct. So which one of the above statements are correct? Option D. 1, 2, and 3. All the three statements are correct. Okay. Question number 60. Which one of the following is a missile follows suborbital flight path with the objective to predetermined target? First, we'll see one by one. So, anti-missile. Anti-missile is designed designed for defense against enemy enemy guided missiles. Enemy guided missiles. So, it's a guided missile which acts as a defense against enemy guided missiles. Whenever there is an enemy guided missiles coming in, approaching, this can hit the target. Next, if you take anti-radar missile, it's a guided missile. It's a guided missile to radio frequencies, detect radio frequencies emitted from the enemy systems, emitted from the radar systems, emitted from the enemy radar systems. So, this is called as anti-radar missile. Cruise missile is also a guided missile used against naval or terrestrial targets. Any region, naval aircrafts or submarines or terrestrial targets, anything naval we use as a submarines where we target that enemy enemy missiles using a torpedo or something like that. Okay, but it stays within the atmosphere. It stays within the atmosphere. Stays within the atmosphere. It doesn't go away from the atmosphere. Okay. So major portion of that flight path, whenever it is flying, the major portion of the flight path is at constant speed. Constant speed. If you take ballistic missile, it's again a if you take a cruise missile, it is always jet propelled throughout the flight. Jet propelled throughout the flight. It is jet propelled throughout the flight. From the way it is jet propelled throughout the flight itself, we can understand that it is laying within the atmosphere. That also within your 25,000 meter altitude. So it is not in the suborbital regime at all. This is again a guided missile, again used for hitting the targets, predefined targets, following an trajectorial approach, not a cruise approach, trajectorial approach like this, hitting the target. Okay. In this, it is jet propelled only in the initial phase, jet propelled in the initial phase alone. Then it enters into suborbital regime, then moves through that, and it's the target or launches in the specified target area. There will be. So among this, only ballistic missile is a suborbital flight path whose objective is for hitting the predetermined target or uh, going to the predetermined target. Remaining all other missiles are also a guided missile only, but it also detects target only, but different forms of target. Okay. And all these the other three missiles stays within the atmospheric layers. So all the other three are wrong options. Question number 111. For an aerofoil, the reaction force resulting from the rate of change of momentum of the moving airstream by the action of aerofoil is deflecting the aerofoil from its original direction. The rate of change of airflow creates not only lift, it also creates drag force also, because when the airflow is moving through, when there is a rate of change of momentum is occurring on the aerofoil, what happens? It also creates lift. Not only lift, it also creates a drag force. Okay. So, so it creates an aerodynamic forces. Lift and drag both are called as aerodynamic forces. So, so it causes both forces, lift and drag. Okay. If you take symmetrical body, if you take symmetrical body when deflected, according to D'Alembert's principle, symmetrical body or any two-dimensional symmetrical body, any two-dimensional symmetrical body will have zero drag according to D'Alembert's principle. So it's not a symmetrical body. They have not talked about anything regarding symmetrical body or unsymmetrical body. So generally an aerofoil, if you take, it's cambered aerofoil we will only use. When the flow is happening on that, there will be both lift and drag acting. Lift and drag is called as aerodynamic forces. So option D is the correct answer. Question number 112. The basic parameters of an hypothetical aircraft are aircraft mass 3000 kg, wing area 75 meters square, CL max is 1.2, maximum aircraft incidence is 15 degree, CL versus uh, CL versus a relationship is assumed to be CL versus alpha. The relation is assumed to be linear. It's not A. Here it is alpha. The relationship is assumed to be linear. Density at 30,000 feet, which is 9,144 meter, is 0.4583 kilogram per meter cube. What is the wing incidence angle alpha when the aircraft is flying at a speed of 80 meter per second, which is 160 knots approximately, at height of 200 feet in the approach to the airfield? 200 meter, 200 feet in approach to the airfield. So first, what are the given data? Then we have to find out which angle it is approaching at to the airfield. What are the given data, sir? Okay. Mass is given 30,000 kg. Okay. If you have to transform into weight, mass into acceleration due to gravity, that is 30,000 into 9.81. Then wing area is given 75 meter square. CL max is given, which is 15 degree, and alpha at CL max, that is alpha stall, is given. Sorry, alpha stall is 15 degree. CL max is given as 1.2. CL max is given as 1.2. Okay. And they have told that at 200 feet, it is approaching the airfield. Approaching the airfield. Approaching the airfield. 200 feet is nothing but, if I have to convert into meter, 1 feet is 0.3048 meter. So multiply it with 1 feet, 0.3048, we'll get what is in meter. So convert that. Now we know what is the temperature, T equal to T naught minus lambda H. So 288.16 Kelvin, lambda is 0.0065, and height is 200 into 0.3048 meter. Substituting that, we get temperature as 287.764 Kelvin. So this is your temperature. Okay. Now density at 200 feet is rho by rho naught is nothing but T by T naught power G by lambda R minus 1. Density at sea level is 1.2256 kilogram per meter cube. Temperature just now we have found out 287.764 Kelvin. Sea level temperature is 288.16 Kelvin. Acceleration due to gravity is 9.80665 at sea level, and lapse rate is 0.0065, and gas constant of air is 287.026 minus 1. Substituting that, we get rho to be 1.2185 kilogram per meter cube. Now, substituting that, we get what is CL. CL is nothing but 2W by rho S V square. 2W by rho S V square, which is nothing but, in a steady level flight, lift is equal to weight. Lift is equal to weight. It is nothing but CL into half rho V square S. So if I keep CL on one side, remaining all the other parameter, I take it on the other side, it will be that. Weight is nothing but the 3000 kg into 9.81. Density is 1.2185. Wing area is 75. And it is approach velocity. V approach is 80 meter per second. It is approaching. So it is 80 meter per second, 80 square. Corresponding CL, we get it as 1.0064. They have told that it is linear. CL versus alpha is linear. CL naught is not given, so we can assume it to be 0. So CL versus alpha is linear. So at 15 degree, CL is maximum, which is 1.2. This is CL max. So lift curve slope, dou CL by dou alpha is nothing but alpha 1 and alpha CL1 is 0. So it is CL by alpha. CL is 1.2. This is 15 degree. So we get the value as 0.08 per degree. 0.08 per degree. Okay. Now lift curve is nothing but CL by alpha. Lift curve slope is 0.08 per degree. CL. CL is at the approach point. CL is at the approach point. CL is just now we have calculated. It is 1.0064 divided by alpha. So alpha is the only thing we have to calculate. So we get it as 12.58 degree, approximately 12.5 degree. So among the answers, if we take option A is the correct answer. Approximately it is 12.6 degree, but the nearest answer we get is 12.5 degree. So option A is the correct answer. Question number 113. Consider the following statements for aerodynamic center of the wing. It is the point about which pitching moment does not change with respect to angle of attack. The aerodynamic center, the definition of aerodynamic center itself, pitching moment coefficient is constant about aerodynamic center. About aerodynamic center, it is constant. Doesn't change with respect to alpha or CL. Doesn't change with respect to alpha, the angle of attack, angle of incidence, or CL. Or CL. So, these statements regarding aerodynamic center is correct. All aerofoils except symmetrical ones, even at zero lift, tend to pitch and experience a pitching moment or a couple. So, if you take symmetrical aerofoil, you at what happens? There will be zero lift at angle of attack. So, what happens? The aerodynamic center always lies for a subsonic airplane. It lies in the quarter chord point, that is 1 by 4 C. So, since at this point only lift is active, initially we assume that it is lift is active. So, what happens for symmetrical airfoils? The pressure distribution is even. So, center of pressure and aerodynamic center point stays same. So, there is zero couple, zero moment is active on symmetrical airfoils. for symmetrical aerofoils. But for all other aerofoils, if you see, for all other aerofoils except symmetrical aerofoils, if you see, what happens is, let us assume a cambered aerofoil. Aerodynamic center, we know that it acts at the quarter chord point. Okay. Aerodynamic center lies at the quarter chord point, which is 0.25 C. Okay. But center of pressure acts somewhere here. So at center of pressure only your lift and drag values acts. Lift and drag acts. Center of pressure only lift and drag acts. Bringing the center of pressure location to aerodynamic center, bringing the center of pressure to the aerodynamic center. So, since center of pressure is a moving point, we have to, for aerodynamic simplicity, we assume that it is lift and drag is acting at aerodynamic center. When lift and drag is acting at the aerodynamic center, shifting this location to this location, that is bringing this lift force and drag force to this location, there is a nose down moment is acted because force into perpendicular distance between this creates a nose down moment. So which is nothing but a pitching moment or a couple. It can they have not mentioned whether it's a nose up pitching moment or nose down pitching moment. They have only mentioned it's a pitching moment. So second one is also correct. All aerofoils except symmetrical ones, even at zero lift, it tends to pitch and experience a pitching moment. Okay. Then option 3. The aerodynamic center is generally around the off chord point of the wing. This only occurs for a supersonic flow. Only for a supersonic flow, this statement can be correct. But in general, we call it's in the quarter chord point. It's not off chord point. Generally, we assume that it's acting at the quarter chord point. So option 3 is a wrong statement. So which means that statement 1 and 2 are only correct. Statement 1 and 2 are only correct. Okay. Question number 116. What is the weight if the pilot will feel on his head while executing a 9G maneuver with an HMD helmet of 800 grams? With an HMD helmet of 800 grams. So it's a 9G force, 9 into 0.8 kg. So it is 0.7, sorry, 9 into 0.8 is nothing but 7.2 kg. So pilot will feel a 9G force means 9 times of its weight on a head. So 9 into 0.8, which is 7.2 kg. Okay. So option A is the correct answer. So thank you.
So thank you guys for watching this session, and if you guys feel this session was useful, you guys can like it, and you guys can also share and subscribe our YouTube channel. And now we have completed all 120 question for DGCA ASO part, so you guys can match with your answers. So thank you all, and tomorrow mostly we'll share the question PDF with answer key. Thank you all. Thank you, Navneet sir, for your
Thank you.
time and
Thank you.
support. So guys, do like if you found this session was useful.
Yeah, thank you guys.